Any questions from the quiz or anything like that you want to take a look at? That was because there was one due yesterday, but we kind of talked about it a little in class yesterday. So, okay. And that one basically went up to the conversation we had up to sort of the compound events like and, or, and then complements, those types of events. Yesterday, what we started talking about was we were looking at the idea of probabilities that can be contingent or conditional on other events happening. So my example was like, I could give you a game and just decide, and then let you decide whether or not you want to bet on rolling a 7. That was one option. Or I could agree to give you a hint and tell you that the dice, I'll agree to tell you whether or not the dice are odd or even when I roll them. And it turns out that if I give you that information and I tell you whether the dice came up odd or even, it actually affects the probability of rolling a 7, right? So then another thing I was looking at was within contingency tables, we were looking at the field trips versus levels of education. And we had looked at this and we had done some probabilities associated with it. Like we looked at an and probability or an overall probability. But then you could also consider, what happens within certain groups and how do certain things affect the probability of other events happening. So, like for this one, we could compute, for example, what's the overall probability that a teacher has taken their students on a field trip, just overall, right? So we've seen this table before, but where is that number at?
32.
Yeah, that's all of these people, right? So our sample size, because there's no condition here, it's not like they have to have a certain level of education or whatever, but so overall there's 51 teachers and 32 took their students on field trips, right? Okay, and you could convert that into a decimal. Let's round it to 4 decimal places, and what do you get?
0.6274.
6274. Okay, so there's like a 63% chance that a teacher takes their kids on field trips overall at these elementary schools in Tennessee. Now what I want to know is, what's the probability that a teacher took their children on a field trip given that they had a master's degree? So it's this given condition. Okay, well, what changes here? Yeah, and so when you have a given condition, essentially you're restricting your sample space. Like your denominator is going to change, just like up here. When I told you that the dice was even or the dice was odd, the denominator is not 36 anymore because there's only 18 possibilities that are odd. Here, our denominator is not 51 anymore. It's 23 because you have to have a master's degree. And then among those, how many went on field trips? 18. What does that come out to be as a decimal rounded to 4 places?
0.7826.
7826. Okay. So what does that tell us about the relationship between a teacher's degree and field trips?
More have a master's degree.
More likely to have a field trip.
If they have a master's degree, they're more likely to go on field trips, right? So what we're seeing here is what you can do is you can compare. This right here, this is a conditional probability. Okay, if we were using our notation, this is like the probability of field trip given master's degree, right? Whereas this right here, this is not a conditional probability. This is just the probability of field trip overall, right? And what we can see is that given that they have a master's degree, so given a master's, that the teacher is more likely to do field trips. Yeah? All right. Does that make sense?
Yes.
All right. I miss field trips. Field trips were awesome.
We should do.
Shouldn't we? We could go to the planetarium and watch a movie.
Okay.
I don't have a lot of statistics movies.
Like if we like take notes on it, could we get extra credit?
Yeah.
We just watch the Red is thesis.
Yeah, we could watch Good Will Hunting, or we could watch. Do you guys watch Donald Duck and Mathemagic Land when you were in school? Did your teacher ever bust that one out on you?
No.
No? Really?
Sounds like something.
Who here's? Has anybody here seen Donald Duck and Mathemagic Land? Oh man, you've seen it like 2 people? Oh, that's a classic.
remember it whatsoever. It's like 7th grade.
Yeah, I don't know. I had one teacher in high school who was just like would play it all the time because she just didn't have anything to do. But Donald Duck and Math, you can YouTube it. It's very riveting. Anyways, yes, okay. I did see it. Oh man, I'll have to find it. I watched a stats video that was pretty interesting. Someday we'll go to the planetarium, maybe. That'd be fun. All right. Anyways, the point is that events. One event can affect the probability of another event occurring. That's the point. Okay. That makes sense, though. So this is one of those. I think the question came up yesterday. Who was asking about the division? Right. Okay, that's Paul.
Yeah.
Paul was asking about, okay, what happens if you don't. His question got at basically, well, what happens if you don't have the sample space information? Because here, I have the whole sample space. I know exactly what's going on. I know all 51 teachers and what they're up to. Here, I know all of my possibilities on my dice and how they could fall out. Well, how do you deal with it if you don't have the sample space? And if you look at the Venn diagram, it'll help you understand you can calculate probabilities conditionally with a formula, but here's how you do it. So let's say that I'm trying to calculate the probability of A given B, right? And remember that the given condition is B, right? So now, if B has to happen, kind of like on the last one, if they had to have a master's degree, we basically could toss out a good chunk of the table, right? We only had to consider this one row on the table. So if B has to happen, so in our picture here, we can toss out most of this picture except for what?
The middle.
Except for, yeah, it's like if B has to have occurred, then it's like what it does is it updates your sample space, right? So given that B has to occur, then now this, we don't have to have a whole big sample space. We have to be in B. Like it's required, right? We can't go outside of that circle with B. So I can ignore, we can just like toss out the rest of our sample space because given B, I have to be inside that circle. Now, you can see from the picture though, where's the only place, we're looking for the probability of A, so where's the only place that it could even occur?
Intersection.
Right. So right here at A and B is the only place A can occur given B. Right? So if you have to be in B, the only way you can also be in A is if you're in the intersection. And so if you think about this, so then the probability of seeing A, given that you're in B, well, your sample space changes. Your sample space would become the probability of being in B. That's like B is your new denominator because B is your new sample space. And then the only way to actually see A occur is to be in the intersection. And so this is the conditional probability formula. If you don't know the sample space, but you know some proportions or probabilities about it, you can calculate conditional probabilities using the formula. Okay, so formulas are always kind of a backup. If you have the sample space, like I know exactly how 2 dice can be rolled. I know exactly how you can draw a card. I know exactly how the teachers look in Tennessee. I don't need to go with formulas. But if you don't have that information, you can fall back on the formulas. And this is the conditional probability formula. Okay? And we can check that it works actually with the teacher one. I think that's what it is. So for example, like I was trying, let's call F equals field trip, and let's call M the event masters, just so I can shorten my notation a little bit. So if I asked you in the last one, we did it with a table, but I said calculate the probability of field trip given masters. That's what we calculated before in the last slide up here, right? Field trip given masters. Well, according to the formula, if say that we didn't have the table, I mean we do, but I just want to show you that the formula works. The way that the conditional probability formula says is it says that you should be able to take the probability of being in both and divide by the probability of a given condition. So the one on the bottom is always the given condition. So if it's given in, it goes on bottom. So if you look at the table, what is the probability of field trip and master's degree? What is that? That's 18 out of 51. And you could approximate it as a decimal. So let's say, what does that come out to be? 4 places maybe. 18 out of 51.
It's 0.3529.
Okay. So, and then we could calculate the probability of master's degree. It's what? 23 out of 51? What does that come out to be?
0.4509.
4509. And so the conditional probability formula says we should be able to take f and m and divide by m. And then if you do that division, what do you get?
0.7826.
Is that what we got before? Yeah. So, same answer. Of course, if you look at it from a fraction standpoint, what happens? Excuse me. Yeah, the 51s divide out. That's a complex fraction. It's another way of writing, or it's actually times. Because it reciprocates when you turn it into multiplication. So the 51s cancel, you just end up with 18 over 23, which is what we knew it should be based on the table. I mean, that's why it works. But anyways, that's not that important. The point is that if you have a table, just use the table. Don't make your life harder than it has to be. But we can use, if we don't have the sample space, we can use summary values to get the probabilities. Like my next example. Sorry, man. I just got this cough that won't go away. All right. Here you go. 33% of students work full-time. 18.6% of students are married and work full-time. What's the probability that a student works full-time given that they are married? Wait, that should be married. Given, wait, did I get that backwards? Oh man, I got this back. I rewrote this one and I think I wrote it wrong. We're going to need this one. That's the way it should have gone. I got it backwards. Okay. What's the probability that they're married given that they work full-time? Okay. So I like to give them letters. Right? So like M, we'll call married. And then we'll call F full-time. Oh, these are the same as the last one, but they mean something different now. So then I just try to figure out, what are we looking for? What probability are we trying to find? What's the probability that they are
Married and work full-time.
married, not and, given, yeah,
Given.
right? Given that they work full-time. That's the way it's supposed to be written. Right, that's what we're trying to find. What's 33.1%? Yeah, and that's the probability of what? That's the probability they work full-time. And then what's the 18.6%?
They're married.
Are married and work full-time. So what's the answer? Yeah, it's a division problem, right? A conditional probability is going to be division. You have to, because I mean the formula is a division problem. The trick is just figuring. Well, and actually this one you can kind of cheat because there's only one way you can divide these. What happens if you divide them the wrong way? You get it won't be negative. So the answer, right? So if you follow the formula, the probability of being married given full time, yeah, exactly.
More than one.
Yeah, the formula tells us if we want to figure out the probability of married given full time, we need to take the probability of married and full time divided by the probability of full time, because it's always the conditional probability on the bottom. And so we're just taking these and dividing. And then what did you say that came out to be? Say 4 decimal places?
0.5619.
5619. Yeah. Something like that. Okay. So a conditional probability is always going to be a division problem. Now in this case, it wasn't too bad because I only gave you 2 probabilities, and you could actually hash out. Because what I was saying is that if you flip that and you divide the probabilities the other way, then you get a number bigger than 1, and that's like a no-no. So you can't do that. Okay. So like OR probabilities always involve addition. Conditional probabilities always involve division. All right. So the conditional probability, let's see what I got here for you. Oh yeah, the conditional probability formula can actually also be used another way. So here's another way, because you'll notice the probability, there's 3 types of probability going on in this formula, right? If you look at the formula, there's a conditional probability, there's an overall probability, and an and probability. So there's 3 types of formulas working, or 3 types of probabilities working together. So realistically, in this case, I gave you 2. I gave you an and an overall. So we produced a conditional. But I mean, I could give you any 2 of those, and you should be able to solve for the other, right? So another way that conditional probabilities can be used is for calculating and probabilities. So here's an example. I'll just let you read it. So let's say H is that they're in the house. And let's say D is that they're a Democrat. So this one, I always, again, I like to assign the letters just because it makes things clearer. Then I like to figure out, okay, so what do I given and what am I really looking for? So what am I looking for? That's the easier one. Well, that's one of these. You see it at the end. What am I looking for?
You're looking for which is a Democrat and a House representative.
Yeah, a House representative and a Democrat, right? So there's 2 chambers of Congress. You got the House and then you got the Senate. So I'm looking for, what's the probability, if I just pick one of them, that I get a House member that's also a Democrat. That's my goal. It might be something like, what? Yeah. What is? So then I want to hash out what I actually am given, though, right? So what's that?
They're actually in the House of Reps.
Yeah. So that's the probability of being in the House overall, right? That's an overall probability. What is this? Of those.
So it's in.
It's a condition. Yeah, that's a given condition, right? It's saying among those or of those, or you could read that as given, right? Given that they're in the house. But this right here, this is a statement, this is a percentage about D, right? It's saying given H, 54% are D. So that's the probability. The given condition there is House, but it's a statement about the proportion that are Democrats. So that's a conditional probability. Can we solve? How? We know the conditional probability. I don't know if this one's going to be division, though. Because the conditional probability formula tells us that D given H should be equal to H and D over H, right? I'm just copying down the formula. Okay, I'm taking it from back here, right? The format is, if you want the probability of an event given another event, it's the probability of both of them happening divided by the probability of the given condition. So in this case, we've got D's and H's going on. Yeah? It's going to end up multiplication because in this case, I don't have the two values on the right-hand side of the equation. One of the values I have is actually a conditional probability. It's D given H. Right? What I'm looking for is this number. But I do have this. So then how do you finish solving it? Well, you just cross multiply that thing up. And so it just ends up being the product of these. So
0.4415.
something like that. Yeah. So, what you do here, so I told you or probabilities always should involve addition, more or less. Conditional probabilities are always going to be a quotient, like you're going to have to divide. And probabilities are typically going to involve multiplication. So, okay. So this is the general multiplication rule. Oh, well, this is not, sorry, let me go one more step. This is not the only way you can solve this problem. And probabilities are also really good candidates for tree diagrams. I think they're really useful. Because what we have here is you basically have a split, right? It's like, a tree diagram helps you map out all, like, the possibilities that could happen, right? Because they could be in the house, or they could not be in the house, right? And then within each of those options, they could be Democrats or not Democrats, right? So there's like the split that occurs. And the way tree diagrams work is you to figure it, like you can go down one path or the other. So like, for example, you could say 81.3% were House representatives. That's the first split. Right? So 0.813. You write the probability or the percentage of the proportion that you go down that route on the branch. Of course, that tells us we know what this number should be, right? Yeah, 187. How do you get it? Well, it's just 1 minus because it's a complement, right? It's not given, but we know it. Then you look at the problem and says, oh, okay, so among those in the house, what's true? 0.543 are Democrats, which means 0.457 of them are not. That wasn't given to us, but we know it has to be true because it's 1 minus, right? And then actually, I don't really know what's going on down here, but I don't actually care. Because where do I want to land? I want House Democrats. So, and the way you use tree diagrams is, so each branch represents a possibility. You could have a House Democrat, a House non-Democrat, a non-House Democrat, or a non-House non-Democrat. There's only 4 ways you can go here in terms of what we're looking for. And so I want to land at the top branch. And the way tree diagrams work is the probability of going down a branch is just the product of the probabilities that get you to the end of that branch. So then you could come to the same conclusion. I can't remember. What was it? 4415? Yeah, because this is 1 minus 0.1813. This is 1 minus 0.543. That's how those numbers got there. Because they're complements, right? And complements they have to add up to 100%. So and probabilities can usually also be hashed out with tree diagrams because you can just start thinking about, okay, well, what could happen here? Could have they could be House representatives or not. They could be Democrats or not. And you sort that tree diagram out. Figure out how to land on each branch. Yeah.
So if that same question were asking us how many are in the House but not Democrats, would we just take 0.813 times 0.57?
Yeah, that's true. It should be whatever's left over from what we just calculated in 81%. But yeah, exactly. You just multiply them. That's true. But again, to calculate an and probability is typically going to involve addition or multiplication. So, yeah. Tree diagrams work in a lot of situations where you have multiple things going on. So here's another example. This one's a fun one. I'll let you read it. So here, you got two types of things going on, right? You got Cokes, you got lemonades, but you're picking two cans. So my question is, what's the probability that both of them are Cokes? What do you think?
So do you do 36 out of 60 and then 35 out of 59?
Yeah, this one's a little different because it's like, you can get a Coke or you could get not a Coke or a lemonade. Because there's only two options, Coke or lemonade, right? So a tree diagram, you think about each branch as a pool, right? And then you can get a Coke or a lemonade, and then you can get a Coke or a lemonade. Well, when you go to pull your first, you can think of it one at a time. It doesn't actually really matter whether you draw them both at once or one at a time. So when you go to pick up your first can, well, how many Cokes are in there? 36 out of 60. That's where your 36 out of 60 was coming. And then 24 out of 60 were lemonades, right? But what happens on your next pull? Your numbers changed and they should have, because, what happened is that if you pick a Coke first, you now only have 35 Cokes to pick from out of 59, right? But you still have all 24 lemonades out of 59 to pick from. And the opposite happens down on the lower branches. If you would have picked a lemonade first, you would have been down to 23 lemonades out of 59 cans, but you still would have had all 35 Cokes in there out of 59. Which branch do I want to land on? I want to land on the top branch. So this is the probability of Coke first and Coke second. So you just multiply across, the probabilities. So you get 36 out of 60 times 35 out of 59. What does that come out to be? Somebody do that for me. You could also say 36 times 35 and then divide by 60, divide by 59.
Do you want it in decimal?
Yeah, let's go decimals. Yeah.
For the one, so how it goes from lemonade to Coke, should that be 36? Or is it
No, because you can't add. It's not like you're adding Cokes in. Are you talking down to the bottom branch?
Yeah.
No, it should stay 35 because. Oh yeah, I'm sorry. No, you're absolutely right. Yes, you are 100% correct.
0.3559.
3559. 3559. Perfect. Thank you. Okay, so that'd be your answer. See, really, but this is actually this is the probability of Coke on your first can. This is actually a conditional probability. This is the probability of Coke second given Coke first. It is a conditional probability. So it's the same format as the last problem we did. We were actually using conditional probabilities. We just don't, in a tree diagram, you don't have to think so much of it as a conditional probability. You can kind of logically think about, okay, well, what happens on the first one? Okay, that affects the second one. One event affects the other. Yeah?
For the
Yes, because here you had 60 cans to pick from at first, but once you pull that second can, everything on this should be 59.
Okay.
And so all of these are actually conditional probabilities. You know, this is Coke given Coke, this is lemonade given Coke, this is Coke given lemonade, lemonade given lemonade. So actually all of those on the second branch are conditional probabilities, even if you didn't recognize it. They're all conditional on what happened in the first round, because it changes. And as you take more and more sodas out of the cooler, they change more and more. Okay. Make sense? Okay. What's the probability that you get one of each? See, this is where, so one thing people want to do is they're tempted to say, okay, so there's a pattern here. It's like probability that times probability that, right? But you have to be careful in a situation like this. Why?
Doesn't matter which one goes first. Is it an or?
Yeah, because, okay, so if you copy it down, right, this was 36 out of 60, 24 out of 60. This became 35 out of 60. This stayed 24 out of, this was 59. Whereas here, this one became 23 out of 59, and this should stay 36 out of 59. That's just copied from the last slide. Now, the thing about it, though, is, how do you get there? Well, you could get there here, right, by getting, Coke first and lemonade second, right? But that's not the only way you could get it. You could get lemonade first and Coke second, right? So it's like either one of these works out. So, well, what's the probability of falling onto the Coke then lemonade branch? You multiply the probabilities. What about the one below it? This one would be what's going to happen here? Can anybody tell? They're going to be the same. Because notice both of those have the same numerators and the same denominators. They're just switched orders, where the 24 and the 36 came from. So 26 times, this 36 times 24 divided by 65 by 59. What does each of these come out to be? 2441.
Yeah.
So there's a 24% chance of one branch, 24% chance you land on the other branch, but both of those branches give us what we want. So what should we do with those probabilities? Yeah, or means what? Add. So you would actually have to combine those branches into, one probability. Because this is like Coke 1, this is lemonade 2 given Coke 1, and then down here it's the opposite. This is lemonade first, this is Coke second given lemonade first. So they're kind of like the reverse scenarios. But they give you the same probability, which they should. But you have to, since both of them are allowed, you have to add them up. Okay, you have to consider whether or not there's multiple ways that could happen. But they're all and probabilities, and they all involve multiplication. Yeah? Make sense? Okay. Probabilities can be complicated. Now, one thing to think about, in this case, with the sodas, right, the outcome of the first affects the second. True?
Yes.
Okay. What about flipping a coin?
No.
Yeah, flipping a coin would be a really boring tree diagram, right? Because what's going to happen?
Same number.
Yeah, it's just going to be 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. It's just going to be a whole bunch of branches with 0.5s on them. So sometimes events affect the probabilities of other events occurring. Sometimes they don't.
Permutation versus combination.
It would be replacement versus non-replacement. Yeah, permutations and combinations are both examples where replace without replacement. They're different types of without replacement.
Okay.
Yeah, it's a question of replacement versus non-replacement. In this case, yeah.
If it can be repeated.
Yeah, it's like if order matters or not. We're going to get into that. That's a side conversation. But yeah, so but the point is that sometimes it matters and sometimes it doesn't. You know, they can affect each other. So this is talking about independence. Okay, so we say that two events are independent if the outcome, or I'm sorry, if one occurring does not affect the probability of the other occurring. So like the example I just gave you is if you think about the events, say heads on your second flip, given the first flip outcome, right? Does it matter, right? So the outcomes of your first flip and your second flip, right? These would be an example of independent events, right? It doesn't matter what happened on the first flip; it doesn't affect your probability on the second one. Whereas the one we just looked at, right? If you look at your type of drink on your second pull versus your first pull, what happens? It changes, right? And so these would be considered not independent, or another way to say that would be dependent. Okay, so what you did on your first pull from the cooler changes what's going to happen in the second pull. What about master's degree versus field trip? What did we find out? Were they independent or not independent?
Oh.
What did we find out? Did the master's degree affect the probability of field trip? Right. Yeah. That was an example where you had dependent events because one happening, whether they had a master's degree or not, actually affected their probability of having a field trip. Whether you got a Coke first affected your probability of getting a Coke second. Whether you got a heads first doesn't affect your probability of getting a head second. It doesn't matter. So
What does the second word say on the second example?
Just type something on the second.
type drink. Sorry. I could have probably written that a lot more clear ways. Here, let's rewrite it. How about Coke first versus like Coke second? That's probably a clearer way to write it, right? Coke first versus Coke second. It matters, right? What happens on the first one matters in terms of what's going to happen on the second one. So it's not, now notice it's different than mutually exclusive. They're not the same thing. Because all of these things are not mutually exclusive. You can get a heads first and then a heads second. Not mutually exclusive. You can get a Coke first and a Coke second. Not mutually exclusive. You can have a master's degree and take your kids on field trips. Not mutually exclusive. But some of them are independent and some of them are not. And so it's a different concept from mutually exclusive. There is a way to check if two things are independent, besides just thinking about it. Some of them are obvious, like the heads, tails scenario. But you can actually check. It's all based on the conditional probability. Okay? Independence occurs when the conditional probability is exactly the same as the overall probability. I'm going to show you what I mean by that. I'll show you an example of that. Okay. So the way you can actually check, if it's not obvious whether two things are independent or not, you can actually check for independence by looking at the overall probability of the events, like what's the probability of the event on its own versus the conditional probability, and see if they're equal or not. And that's actually what we did in the field trip example. We just didn't realize it at the time because we hadn't talked about independence versus non-independence. But if you go back to that field trip example, wherever we started, there it was. See, this is the probability of field trip overall, right? Whereas this is the probability of field trip given master's degree. And what do you notice? The probability of field trip changes with the given condition. So they're not independent. Okay, they're not the same. I'll show you an example where it is the same. It's kind of trivial, but we'll go back to drawing cards because it just makes a really easy way to display that. Okay. All right. So we looked at some of these already. I think we already used these examples, but let's say these are advanced. Okay, so not too hard. Probability of king, what's it going to come out to be? Right? 4 out of 52, because there's 4 kings out of 52, which is just 1 out of 13, right? Probability heart.
1 out of 4.
Yeah, 13 out of 52, which reduces to 1 out of 4. Probability of red. 26 out of 52, which is the same as 1/2, right? Those are just overall probabilities of pulling those cards. Okay? All right. Now what I want to do is I want to look at some, which of those events do you think are independent and which of them do you think are not independent? Like, does being a king affect the probability of being a heart? Does being a red affect the probability of being a heart?
No.
Does being a heart affect the probability of being a king?
You're asking a lot of questions.
Okay. Right. So, well, that's okay. So it's kind of like the game, right? It's like, let's say you're going to bet on kings. Like, will it help you if I tell you whether or not it's a heart? Is that going to give you additional information? I don't know. Let's see.
Yeah, it depends on if the king's been called the king of hearts. Is being called.
No, it's just like one card. Just one card.
Oh.
So all of them are in the deck. I'm going to pick one. And you get to bet on one of these. And the question is does knowing one of these events affect the probability of the other events? And I think the answer is sometimes yes and sometimes no. Some of these are independent and some of them are not. But the way you can know for sure is you can look at the conditional probabilities. That's the key, right? So we just figured out, right? King was 1 in 13, right? I'm going to copy those over. Heart was 1 in 4. And red was 1 out of 2. That's where there's reduced form, right? So what we can do is we can say, okay, well, let's look at the conditional probabilities. So, king given heart. So the conditional probability, remember what it does is it restricts the sample space. It changes the denominator. So if it has to be a heart, how many are there? 13. How many of those are kings? 1. If it has to be a king, how many are there? 4. How many of them are hearts? 1. What do you notice?
It's going to be 1.
Yeah, isn't this exactly the probability of king overall?
Yeah.
And isn't this exactly the probability of a heart overall? Did I go too fast?
No.
Because given, yeah, so just real quick. So given a heart, how many cards am I stuck with? 13. That's where there's a 13 on the bottom. How many of them are kings? There's only 1. If I tell you I have a king in my hand, I could only be holding how many cards? 4. That's why there's a 4 down there. How many of them are hearts? Only 1 of them could be a heart. 1 and 4. But if you compare them to our overall probabilities that we calculated on the last slide, Well, 1 in 13, that's just your overall chance of getting a king. In 1 in 4, that was your overall chance of getting a heart going into it, even if I told you nothing, right? So did my hint give you any information? My hint was useless, right? And so then it looks like that king and heart are independent. So knowing whether one's a king doesn't help you know whether it's a heart, and knowing that it's a heart doesn't affect your probability of pulling a king. They don't give you any useful information. So I might as well not tell you at all. Okay. So I could offer it to you as a hint, but in reality I'm not doing you any favors. Okay, so now think about the next one. Okay. Given that it's red, how many cards am I dealing with?
26.
Yeah, half the deck. There's only 26 red cards. Now how many of them are hearts though? 13 of them. So what's the probability of heart given red? 1/2. So if I tell you it's red, what have I done to your probability of a heart?
Double increase.
I've increased it because when you started out, you only had a 1 in 4 chance of pulling a heart. But if I tell you that I'm holding on to a red card, I've actually increased your probability to a 50-50 shot. And if you look the other way, if it's given that it's a heart, how many cards are out there?
13.
Yeah, if it's given heart, there's only 13 cards I could be holding on to. And how many of them are red? All of them. So what does your probability bump up to? 100%. And so this is not the probability of heart overall. This is not the probability of red overall. By telling you information about the color or the suit, they affect each other. So in this case, we would say that H and R are dependent. So that actually, if I was going to offer that hint to you, you should take that hint. It's very useful. Okay. How about this one? Given that it's a king, how many cards could I have in my hand? How many are red? Could be 2. So what's my 1/2? But what was my probability of red at the outset? 1/2. Oh, whoops. I didn't mean to write the same thing twice. This was just the probability of red to begin with. What about if, given that it's red, how many cards could I have? 26. How many of them could be kings? There's only 2 red kings. But, so 1 in 13. But wasn't that just my probability of king at the outset? So what's true here? Yeah, these are independent. That doesn't even look like a word. Just get rid of it.
So you just have to look at like the second letter first, or variable I should say, to see like if it affects the first one in any way, and then that would
Yeah.
determine if it's independent or dependent.
Mm-hmm.
Okay.
Does it affect its probability?
Huh?
Excuse me, sorry, I think I'm losing my voice right now. Does it affect its probability?
Yeah.
Yeah. Does one event affect the other's probability
Yeah,
of occurring?
That's what I'm saying.
Yeah. Mm-hmm.
I looked up probability.
Yeah. It's like if you look outside and there's clouds in the sky, does it affect the probability of rain?
Yeah.
It does. The presence of clouds affects the probability of rain. Because if there's no clouds, it's like almost a 0% chance probably. I don't know. Maybe it can rain without clouds. I don't know. But if there is clouds, it ups your probability or something. So, yeah? So it's a relationship between conditional probability and overall probability. So if knowing one changes the probability that they're occurring, then they're dependent. But if it doesn't help you out, then they're independent. They don't inform each other. So, okay? So far, so good. It's getting fun, right? Mm-hmm. I'm telling you. So probability is it's a side trip, but, you know, we really need to think. It's not trivial information. This is good to know because we deal with conditional probabilities all the time. I mean, like, we're always dealing with conditional probabilities. You know, so anyways, so the point is we already kind of saw this. So we know the general multiplication, here's the general multiplication rule. So we saw from before that we can calculate and probabilities, right? You can calculate and probabilities by taking the probability of an event. So like if you think back to the tree diagram, like A happens or it doesn't, and then B can happen or not happen. But like this, if B is conditional on A, then you would take the probability of A and then you multiply it times the probability of B given that A occurred. Or if you had the other way, it could be B times A given B. Either one of these works. So I should say or. Right. So this is the general multiplication rule. We already used that one before with the senator example. And you need this, and this is really important. You have to do it this way you need this if A and B are dependent. You have to think about conditional probabilities if they're dependent because the order matters. So if the given condition is A, then you should be multiplying the probability by A, but if the given condition is B, you should be multiplying by the probability of B. But if they're independent, things get nicer. All right, I think we have just enough time here. Let's see. Yeah. So here's an excellent example, and the order matters because there's 4 probabilities right there, right? You only need 2, but it's possible that you could have 4 different probabilities in place. So here's an example, because like if I look here, so he says what 30% claim they don't send or read text message while driving. 47% of drivers are over 40. Of those that claim they don't text and drive, 70% are over age of 40. What percent of the population is over 40 and not texting? Okay. So I'll say O is over 40. And let's say N is not texting. Okay. Now what probability are we trying to find? And, right? So I'm looking for the probability that they're over 40 and not texting. Now I know an and probability should involve multiplication. The problem is that there's 3 probabilities in this problem, and I only need 2 to multiply. So the question is, which 2 probabilities should be multiplied, and which probability here is superfluous, unnecessary?
30%.
Why is it 30%?
Because that's overall 47 was only when it affects the 40 and over.
Let's see.
Did I have it wrong?
I don't know, because that's the thing about the formula. See, the formula says we're going to multiply something here, but it's either got to be the probability of O times the probability of N given O, or it could be the probability of N times the probability of O given N. The general rule says it could be either one. The question is, I only have 3 probabilities. I don't have 4. So which one is it? Which 2 should we use? And so this is why I like to list what I have. So what is 30%?
Overall drivers.
That's,
Not syntax.
yeah, we could write that as P of what? 30% say they never send or text.
N.
That's P of N. Okay, so I know I have that value, P of N. So could maybe use that. What is 47%? Yeah, that's P of O. All right. What is this?
That's given, like they're over the age of 40.
What's the given
Oh,
of those?
It's P of N given O.
Given given of those, given
And of,
that they don't text and drive.
Oh, sure.
It's the flip. What's the given condition here? This is given they don't text and drive. Not texting is the given condition there. The percentage, it's a percentage about how many are over 40. So it's a probability about being over 40, but with the condition of not texting. And so it's O given N. Right? So we have the P of N, we have P of O, we have P of O given N. What we don't have is we don't have that value. So it's actually the P of O is the superfluous. The P of O is the extra information. We can't use it because we don't know N given O. So then we'll use the probability of N times the probability of O given N. And so the answer should be 0.21? Do it like that. Okay. Recognizing the given condition, if you recognize the given condition, you could hash it out like a tree diagram, because if the given condition is that they don't text and drive, right, then that's this number, 70%, and then we could see that we need to use the non-texting population, if you recognize that the given condition is the one that has to come first on the tree diagram. So if the given condition is a statement about whether they text and drive or not, the first step in the tree diagram should be a step about them not texting and drive. You know what I'm saying? So the given condition should come first on your tree diagram. But either way, it's multiplication. All right? Are we out of time? We are. We are out of time. I think that's about it, though. Oh, yeah. There's like one slide left, but that's pretty much it. All right.